Hello everyone, and welcome to my 14.4 pre-class video. And I thought an excellent idea as far as what we should cover in this pre-class video would be actually to drop back down to Calculus 1, where we talked about linearizations and tangent lines originally, and how these can be used to approximate functions' values. So that's what I would like to do, because that's what we're going to be upgrading essentially here in this class to a multivariable sort of situation. And so I have here the function square root of x, right? And so I have the square root of x, and then I also have the tangent line right here, which we also can call the linearization equation. So notice that this is the function's height right here, f of a, plus, so this is the slope, m is the derivative, times x minus a. So this right here is exactly the line that goes through this point here. And we would get a lot of questions back in our Calculus 1 days that said, we want to approximate something like the square root of 4.1. Now, of course, now because everything's online, right, we have a calculator, but kind of initially and originally you should be thinking about these. I mean, solving these back in like the 1600s, 1700s, right? You don't have a calculator. You have to try to come up with your best approximation for the square root of 4.1. How do you do that, right? And so you say, well, the square root of 4 is 2, so it's a little bit bigger than 2. But let's suppose that you wanted to get a better approximation for that, right? Something, a little bit more refined than, oh, it's bigger than 2, right? And so the way to do this, or a nice way to do this anyway, and let me go ahead, I want to draw a line really quick here at 4.1, just so we know where we should be looking, is that instead of, right, the square root can be quite difficult for these decimal numbers like 4.1, or imagine like 4.01 or things like this, right? The square root can be quite difficult. There's a lot of guess and check that would have to go into this in order to solve that, right? What when squared would give 4.1. And so a way to get a good approximation is, instead of using this blue curve, which, remember, the blue curve right here is the square root function, and the green curve here is the line. So, right, instead of using the actual square root function, this blue curve here, why not use the green curve? Because you can see that the blue curve and the green curve, so long as you're relatively close to this point here, that the blue curve and the green curve are very, very close to one another, right? They're not off by much at all. So in reality, the square root of 4.1 is actually this right here, 2.0248. That's what the actual blue curve, the square root function is. And of course, there's more decimals that, this would probably just keep on going on. But the green curve would say, well, a good approximation for this would be 2.025, right? So it just seems like it's off by what? That's not even thousandths. Those are 10,000ths, right? So this isn't off by much at all. And so the linearization equation, this tangent line, can be used to approximate things that are quite difficult to calculate. And that is exactly what we want to do now in a higher dimensional sense. So let me go ahead. I'm going to stop sharing really quick with my desktop here. I'm going to start sharing with my iPad, just so I can jot down a few things. So remember, the tangent line equation originally came from the point slope formula, right? So you had something like this: y minus some y point is equal to m times x minus some x point. And then if you say, well, this is actually on a function, right? And so suppose that we're interested in the point a comma f of a, then this is your x special point, and this is your y special point. So you could plug those things in. So you would get that this is y minus f of a is equal to m times x minus a. And then if this is supposed to be the tangent line, right, the slope here is something special for the tangent line. It's the derivative. So this is going to be the derivative at a. So you'll notice in what I was graphing, that equation was just the equation of the tangent line. I moved f of a over so I could get a y equals sort of setup. It's just the equation of the tangent line, but this is what we often call the linearization equation. This is a function in its own right. It's a nice straight line because we have some intercept, some slope, and this x minus a sort of business here. So that is the linearization equation. That's that L of x that I had graphed on my desktop on Desmos there. And so now, if we were talking about a higher order linearization, these are going to be tangent planes. So now we might have z as a function of maybe x and y. And maybe we're interested in a tangent plane at a particular point. So maybe we're interested in, I don't know, maybe the x value is a, the y value can be b, and then the z value, well, you just plug those things in because it's on this function. So this is going to be f of a b. So again, this is very similar to what we did right up here, but now we have more variables. We have x, y, and z. So, okay, so that's kind of the setup here. And if you could imagine just kind of an extension of what we have here, it's going to go something like this. Well, first of all, the linearization is going to depend on now two variables. So instead of just L of x, it depends on L of x and y. So this is how we do the multivariable case. The function's value is now at a comma b, because again, there's now two inputs to this. And then you get to this bit here, right? How do we account for this in a multivariable sense? And the answer is to do kind of a fairly natural thing, right? Now that we have two variables, we have to sprinkle in the derivative with respect to both of those variables. So before we only had one variable, that's just f prime of a. We take the derivative with respect to x at a, and that's it. But if you have more variables, well, let's go ahead and take more derivatives. So maybe we can talk about the x case. So when we take the derivative of our function with respect to x, of course, we have to plug in our specific point. So just like we did at a here, our specific point is ab. So we'll plug that in. And then that one, we're going to go ahead and multiply by x minus a. And then if you go ahead, right, we took care of the x variable, but why was x special? We have to take care of the y's as well, right? So now we have to add also, and this is the extension here, we need to add on the derivative of f at y, and then we're going to multiply that by y minus its special point, right? So again, the x special point was a, so these are our x variables, these are our y variables, and these are our z variables here. So x, y, z. So that's why we do y minus b there. So this right here is going to be the linearization equation now for two variables. But from this, you can also see if you wanted three variables or four variables, right? What the pattern is in order to extend this to as many variables as you want. So this is just for two variables. This is going to be, by and large, what we're using in this class. But you can imagine, right, if you wanted to use this to approximate something, well, very similar to this tangent line equation back here, right? You could just plug things in to the tangent plane. So likewise, not only this is the linearization, but this is also a tangent plane. So this right here is the tangent plane equation. If you want to, you can write this as, right, this is a z value here, so z equals. And yeah, so that's kind of the setup, and that kind of how it relates to what we've done back in our Calc 1 days. So I hope that this has been useful and that you've enjoyed this video. I'll see you guys next time. Take care.